Chapter 9, Section 3, Rotations. A rotation of x degrees, so however many degrees, about a point Q, rotations are always going to be about a point, called the center of rotation, so that point is the center of rotation, is a transformation in which the image of Q is itself, so if you're rotating it about a point Q and Q is on the figure, Q stays itself. And for any other point V, QV prime is equal to QV. So in other words, let's say we were rotating something, and we'll see an example of this, about the origin, so about that point. If this was V and this is V prime, the distance from the center of rotation from V to the origin is going to be the same distance as from V prime to the origin. And the measure of the angle, V, and let's say this point is Q, so V, Q, V prime is going to be x degrees. So however many degrees the rotation is should be the measure of the angle from the pre-image to the center of rotation to the image. The number of degrees a figure rotates is called the angle of rotation. A rotation about a point is a rigid motion, and it preserves distance, angle measure, collinearity, and midpoint. Orientation is also preserved, so rotations are direct isometries. Now, as for rules, a rotation turns a figure through an angle about a fixed point called the center of rotation, as we said before. A positive angle of rotation turns the figure counterclockwise. This is really important. You're always assuming that you're rotating counterclockwise. So if it's a positive angle, you're rotating counterclockwise, whereas a negative angle would be turning it clockwise. And as we said before, it is a direct isometry. Now, if we did a rotation of 90 degrees, what happens is the x and y coordinates switch places, and you negate the y coordinate, which is now in the x place. So if we start off with a point and we're rotating it 90 degrees, and they're all going to be about the origin for the ones that we're doing here. Let's say we have the point 3, -4. Our new point is going to be +4, 3. So they switch places, and you negate whichever number is going into this place. Now, if we're doing 180 degrees, rotating it is going to just negate the x and y coordinates. So this is going to be a similar rule for a point reflection, but we haven't really talked that much about that. A point reflection would be if we were on a coordinate plane and we reflected it across the origin. That would be, let's say, this point across the origin. If this point was -3, 4, we would get 3, -4 when we did a point reflection. So they have the same rule. So rotating 180 degrees, you just negate the x and y. Finally, rotation of 270 degrees, you switch places again, but this time you negate the x. So if we're rotating 270 degrees, again, that would be a counterclockwise rotation of the point 7, -3. Our new point of our image would be -3, -7. So they switch places, and you negate the one that's going into this spot. So if we look at some of these examples, and this should be done on graph paper, separate sheets of graph paper. A rotation of 90 degrees, this means about the origin of xy. You switch places and negate the first. This angle, so this is our pre-image, this is our image. This angle is 90 degrees because we just did a 90-degree rotation. Here, a rotation of 180 degrees about the origin of point G, so 2, 3, you negate the x and you negate the y, and you get -2, 3, and this angle is 180 degrees, so it's a straight angle. If we're rotating it 270 degrees about the origin, we switch their places and we negate the x value. This angle measure is going to be 270 degrees. And finally, a 360 degree rotation just gets you back where you started. So G and G prime would be the same point. Now trying this example, we have quadrilateral PQRS and it has vertices with these coordinates. We want to graph a 90 degree rotation about the origin of quadrilateral PQRS. So this should be done on graph paper as well. First, you graph the pre-image and then the images for each vertex. So first plot the points for the pre-image. We're rotating it 90 degrees, and that's always counterclockwise. What happens for our 90 degree rotations, as we said. By the way, rotations are normally a lowercase r and reflections are a capital R. But either way, we know that if it's an angle measure, that's going to be a rotation. So that's going to change our coordinates from x, y to negative y, x. So they switch places and you negate the one that's in front. So 1, 1 becomes negative 1, 1. For Q prime, 3, 3 becomes negative 3, 3. For R prime, 4, 1 becomes negative 1, 4. And for S prime, 3, 0 becomes 0, 3 because you can't have a negative 0. So it's just 0, 3. We plot the points, so P prime, Q prime, R prime, and S prime. We connect the vertices, and now we have our image. And you can see that we're rotating it about the origin from P to the origin to P prime. This is a 90 degree angle, and it should be. So from the pre-image to the origin to the image makes a 90 degree angle because it was a 90 degree rotation. Now, you don't actually have to construct this, but I do want you to just point out how this would be done, maybe make a few notes on it. If you're rotating an image 100 degrees about point C, in order to do this, if this was our pre-image and this was our center of rotation, we would have to draw CO. So we draw that line first. And this is step 1. Then we'd have to use a protractor to draw a 100 degree angle, and that can be seen here, with vertex C inside CO. Then we would use a compass to construct CO. So CO prime is going to be the same distance. So we'd measure this and copy the segment here, and then we'd have CO. Then we'd do the same thing with CL. We'd copy this distance, copy this line, and finally the same thing with CB, copy this distance, copy this line, and then we'd connect our 3 points, 3 vertices, and that would be our image. So this would be possible if we had a protractor and a compass. We're mostly just working with compasses, so we'll mostly just be constructing reflections and translations. Now, just to go back a little bit, talking about reflections, rotations, translations, a figure is said to have line symmetry when the figure is its own image under a line reflection. So like a butterfly. This side is symmetric to this side, and the whole thing makes up the image. So this image has line symmetry because if you break it in half, this side is symmetric to this side, and it makes up the whole. The letter A is another example of this. This side is symmetric to this side, and when you reflect, let's say, the left-hand side over this axis of symmetry, you get the whole letter A. Now, a figure is said to have point symmetry if the figure is its own image under a reflection in a point. So if we let P be the center of any circle, and A be any point on the circle, we can see that under a point reflection, A would be mapped to B, and any other point would be mapped to a point on the opposite side. In other words, we know that all points in a circle are equidistant from the center, any point on the circle would be reflected to the other side of the circle under a point reflection. So a circle is an example of something with point symmetry. The letters S and N also have point symmetry, as does the number 8. A figure is said to have rotational symmetry if the figure is its own image under a rotation, and the center of the rotation is the only fixed point. So if this is our center of rotation, if we rotated it counterclockwise, we would get a star. So if we rotated this figure counterclockwise, we would get the star. So rotational symmetry, a star is said to have rotational symmetry. And then translational symmetry is if the image of every point of the figure is a point in the figure. A good example for this is wallpaper or borders. So it's translated multiple times, obviously, here, and it makes up the whole image.